Good evening, everyone, and welcome to Arlington's David M. Brown Planetarium. My name is Rafael Perino. I'm a board member for Friends of Arlington's David M. Brown Planetarium. Happy to have you here tonight. We have quite a treat for you. In from NASA Ames Research Center, NASA Kepler Mission Scientist Natalie Batalha will be speaking about the Kepler mission. So I know that she has amazing things to talk about with regard to Kepler and the booming field of exoplanet research. So enjoy.
Hello. Is my mic on? Yes. You guys can hear me okay? All right. Thanks for inviting me. It's a pleasure to be here. I don't get out to the East Coast very much, let alone to planetariums. This is a real treat. As Raphael explained, I'm here to talk about NASA's Kepler mission. How many of you have heard of Kepler? Not the man, the mission. Less of you. Okay, well, I'm glad you've heard of Johannes. That's great. Okay, well, how many of you have heard of an exoplanet, what an exoplanet is? It's a planet, but we put the word exo or the prefix exo in front of it to say that it's outside the solar system. These are planets that are orbiting other stars in our galaxy, not planets in our own solar system. So we're looking for other worlds out there. NASA is literally on a quest. In fact, maybe I should say humanity is on a quest to find evidence of life beyond the solar system. Not just you and me here on this planet, but beyond the solar system on planets orbiting other stars. And this is not science fiction. It's not a pipe dream. This is something that is really going to happen. We have a roadmap. In fact, an official NASA 30-year roadmap was just released about a week ago, or just before Christmas. And in that roadmap, it lays out a plan for how we can find evidence of life beyond Earth. There are kind of three paths that we could take. You can explore the solar system, maybe someplace in the solar system, lurking someplace, maybe beneath the soil of Mars, or maybe on one of the moons of Jupiter and Saturn, underneath the ice. Maybe there's an ocean where there are creatures living. Maybe there's life in the solar system. So that's one option, is to explore our own solar system. Another option is to do what SETI does, the organization that listens for signs of intelligent life out in the universe through technological signals, some kind of a signal that's beamed through the galaxy that is not due to nature, to normal astrophysical sources, right? And the third option is to find potential cradles of life. Other worlds like Earth where the conditions are right for life as we know it to exist. And that's the path that I'm going to tell you about, searching for exoplanets. Okay? So the title of the talk is A Planet for Goldilocks. All right? So in honor of the kids, we're going to start with a fairy tale. Once upon a time, there was a little girl named Goldilocks who wandered deep into a dark forest. And in the middle of that forest, she came upon a little house. And so inviting it was, she couldn't help but go up and go inside. The door was unlocked, and in the kitchen she found foods laid out on the table. One of the pots of porridge was too hot and she burned herself. The other was too cold. But the third was just right, and she ate it all up. Tired from her wandering, she went into the living room, and there she found 3 chairs, but one was too hard, one was too soft, but the third one was just her right size, and she rocked and rocked and rocked, so much that the chair fell apart. Still tired from her wandering, she went into the bedroom, and there she found a bed, too hard, another bed, too soft, and a third bed just right, and she curled up into that bed and she fell fast asleep. Now, Goldilocks ended up running home in terror that night, afraid and awoken by 3 bears who scared her, and she left that little house in the middle of the forest. So we're going to come back to this story of Goldilocks at the end of the talk. But for now, I want you guys to have this idea of a just right place. Things that are just right. just right for us, just right for creatures, just right for life as we know it here on Earth. We're looking for planets for Goldilocks. Well, what is a planet for Goldilocks? What do we need for that planet to be just right for life? Planets come in all different sizes, different temperatures. They're made out of different things, and Goldilocks is looking at this huge diversity of planets, even in our own solar system, and she's wondering, well, what is just right? Well, it can't be too big, and it can't be too small. If a planet is too big, too heavy, it's going to attract through the gravitational force a lot of hydrogen and helium that ends up turning it into a giant gas planet like Jupiter and Saturn, or Neptune and Uranus. If a planet is too small, it's not going to have enough gravity to hold on to any atmosphere at all. There's not going to be anything there to breathe, kind of like on the Moon and Mercury. So we want a planet with kind of just the right size. We also want a planet with just the right temperature. We don't want it to be orbiting too close to the star because it's going to be burning hot. All of the things that we want for life, water, for example, are going to boil away. We don't want it to be too cold because then water is going to freeze up. We want it to be just right. And so I've already mentioned this idea of water being one of the key ingredients for life. But that might not be obvious. What is required for life here on Earth? If I ask you guys what's required for life, maybe you'll say, what, pepperoni pizza? No? Video games. Facebook. Is that it? Everybody has a different answer. And in fact, creatures on planet Earth are very diverse. There are creatures living in all different nooks and crannies here on planet Earth, and they all require different things. Right? Some creatures don't even need oxygen to breathe, even though we do. Some creatures don't need sunlight, even though we do, and plants do. But one thing that all creatures on planet Earth have in common is that they are made primarily of carbon. They're carbon-based. And carbon-based chemistry, as we understand it, or as we know it, requires as the solvent to facilitate important chemical reactions like metabolism, liquid water. Okay? So we think that even though all of these creatures on planet Earth are so diverse and they all need different things, the one thing that they all have in common is that they need liquid water. So we don't want the planet to be too hot where the liquid water is going to boil, and we don't want it to be too cold where it's going to be frozen. We want it just right. And that means the planet has to be at a certain distance from the star. All right, well, what are these planets? This is a little cartoon of a star like our sun, and in front of it, sitting on the table, are little balls representing the different planets of our solar system. And you can see that how tiny they are compared to the star, right? Planets are like just the leftover junk. Planets are like an afterthought of star formation. They're the debris that's left over. They're the stuff that your mom would sweep under the carpet. It's nothing. Right? And if you're talking about a planet like Earth, which is here, look how tiny it is in comparison to the star, right? So planets are going to be really hard to find. It's going to be very difficult to find planets orbiting other stars that are so far away. And those stars are very, very faint compared to the glare of the star that they're orbiting. They're literally lost in the glare of their parent star. So it's not like we can just point a telescope and take a picture, right? It's kind of like having this big, giant searchlight or lighthouse, and you're looking at it trying to see a firefly that's there, right? It's hidden. The planets are very faint, and the star, the central star, is very bright. So they're lost in the glare. We can't just take a picture. Well, we have for some cases, but in general, that's not the rule, at least for now. Most of the planets that we have discovered to date have been found by indirect means. By observing the star itself and observing some characteristic of the star that helps us to infer the existence of the planet. Okay? And this is one of those methods. In this cartoon, we have a star, and we've got this little ball orbiting around it, just as planets do. And we all know that planets orbit their stars, but perhaps it's not so obvious that stars also orbit their planets. Both of these objects are moving. They're orbiting about their common center of mass. If you could imagine a rod connecting the star and the planet, and you were going to put your finger on that rod in a position that would perfectly balance them so that they would be balanced on your finger, that's the center of mass. That's the point about which both of these objects orbit. The center of mass is going to be very close to the star itself, right? So the star moves just a tiny bit. The planet moves a lot as it goes around your finger. And so if we can somehow make an observation of the star and see that it's wobbling, we can infer the existence of some massive body there that is causing the star to wobble via the gravitational force, right? So that's the wobble. Again, we're not going to take a picture and watch the star and see it actually wobble on the sky. What we're going to do is we're going to take some of the biggest telescopes in the world, these eyeballs to the universe that extend our senses out into the universe. These are the twin Keck 10-meter telescopes on Mauna Kea in Hawaii. They collect light from distant stars, and we're going to take that light from the stars, collect it, and we're going to spread it out into a rainbow, right? You guys have had crystals hanging in your window. When the sunlight catches it, it creates a rainbow, right? We're going to do the same thing. And here's what that rainbow of starlight looks like. Red, orange, yellow, green, blue. And if you stare at it, you see all those beautiful colors, but you also see some black gaps, places where there is no color, right? Those black gaps where there's no light are called absorption lines. Those are colors that the atmosphere of the star liked a lot. The atmosphere of the star absorbed those particular colors, taking them away so that they don't reach your eye. So you've got this place where there's this absence of light. And those absorption lines are important because as the star wobbles on its axis, when we take its light, spread it out into a rainbow, and we look at where that missing light is, we're going to see that it moves back and forth as the star wobbles. Okay? Let's look at an animation of that. Let's look at one of these lines. See how it's black? There's a grid underneath it of detectors that are measuring the brightness of light falling at that particular color. And as the star wobbles around, the place that's black is moving back and forth. And this is called the Doppler Effect, and we can measure this. And how much it's moving back and forth tells us how much the star is wobbling and therefore how massive the planet is that's orbiting it. And this is called the Doppler method. Many hundreds of planets were discovered using this method. So each of those detectors is simply measuring a different amount of light, and we see it wobble back and forth. We see it slosh back and forth. This is a cartoon from a popular site called XKCD. It's about a year old, maybe a little bit longer, a year and a half. As of June of 2012, there were 786 exoplanets known orbiting other stars, known to humanity. And so every circle that you see there is one of these planets orbiting another star. And they're all sized according to how big the planet actually is. In the middle here, there's this little gray square. Those are the solar system planets. And the two biggest ones in our solar system are what? The two biggest planets in our solar system are, do you guys know? Jupiter and Saturn, that's correct. Okay, so look at Jupiter and Saturn in that tiny square and then scan your eye over the rest of the cartoon. You notice that most of the exoplanets that have been discovered so far are actually bigger than Jupiter and Saturn, right? And that makes sense because those are the easiest ones to find. They are really massive and they pull on the star a lot. They make it wobble a lot, and so it's easy to see those stars wobble. They're the easiest to find. But what we want to do is we want to find places where life can exist. That's not going to be planets that are larger than Jupiter and Saturn, at least not life as we know it, right? We want to find planets like Earth. And so that's why NASA decided to fund this spacecraft called Kepler. Here's a cartoon of the Kepler spacecraft. It's a telescope that's out in space, looking at stars, trying to find planets. And Kepler is supposed to answer one really simple question. What fraction of stars in the galaxy harbor potentially habitable Earth-sized planets? If we can answer this very first question, then it'll give us some indication of whether life in the universe might be ubiquitous or common, right? First, we have to know if the cradles of life exist. Okay?
3, 2, engine start, 1.
Kepler was launched in March of 2009 from Cape Canaveral in Florida. This is the spacecraft. I was there. There were some people in this audience who were there as well. We watched it launch at night. It was launched into an orbit outside of the Earth's gravitational pull. This telescope is actually orbiting the sun, not the Earth. It's been operating for 4 years. It collected 4 years of data, which is the amount of data that NASA wanted it to collect. And it stared at this region of the sky. Near the plane of the Milky Way galaxy, in the summer, you look up and you can see these 3 bright stars, Vega, Deneb, Altair. That's the summer triangle. And between Cygnus the Swan and Lyra is this pattern, which is this mosaic of detectors. The starlight falls on these detectors, and that's what measures the amount of light coming from the star itself. This is NASA Ames. This is one of the computer centers at NASA Ames, and here I'm pulling up the very first picture that Kepler ever took of this one piece of sky. Every tiny little white speck you see there is a star in our own galaxy. And that patch of sky is only about the size of my hand projected onto the sky. There are 4.5 million stars in this one picture alone in our galaxy. So before Kepler launched, we used ground-based telescopes to observe all of those stars. And we cherry-picked the ones that are kind of like our sun, the ones that we thought would have the best chance of showing us indication of a planet. Okay, so how are we going to find those planets? Well, here is an image of the surface of the Earth. And there's this black spot on it. Do you guys know what that black spot might be? Do you have any guess? Who has a guess? What is that black spot? Yes?
Ocean.
An ocean? No, it's not an ocean. That's a good guess. It kind of looks like an ocean. Yes, over there.
Shadow of the moon.
It's the shadow of the moon. That's right. Every object orbiting a bright star actually casts a shadow out into the galaxy, always. Our moon is casting a shadow out into the galaxy. Our own Earth is casting a shadow out into the galaxy, right? And here, the surface of the Earth actually happened to catch the shadow of the moon. We kind of forget that our own Earth is actually casting a shadow until we have an eclipse of the moon, a lunar eclipse. Right? Then we see our own shadow sweeping across the face of the moon, our shadow that's cast out into the galaxy. It sweeps across the face of the moon and we see ourselves there. So all of these planets orbiting stars are casting shadows out into the galaxy, and Kepler is going to catch them. It's going to look for these shadows. There's Kepler, an animation of Kepler looking at the stars in our galaxy, and if we zoom in to one of these distant stars, we see that it actually has a planet orbiting it. And if that orbit is just aligned just right, when the planet passes between the star and our telescope, it's going to cause a momentary dimming of light. So the light goes into the telescope, we measure the amount of light coming from that star very accurately. This is an image. Each one of these white specks is a star. This is zoomed in, and you see it's kind of pixelated. So what we're actually doing is measuring the brightness. We don't see a picture like this. We have brightness measurements. And as we plot them out as a function of time, When the planet goes in front of the star, the brightness is going to fall a little bit, and we call that a transit. It's a dimming of light that happens when the planet passes in front of the star, because the planet is casting a shadow out into the galaxy, and that shadow is sweeping across the face of the telescope. And so we see that as a momentary dimming of light. Okay? So that's how we're finding these planets. We're looking for these transit events. So the amount of dimming that you get tells us something about how big the planet is. If you get a big dimming of light, it's a planet like this, like Jupiter. That's about a 1% dimming of light. This is what an Earth looks like. It's very, very tiny. It produces a dimming of light that's like 1 part per 10,000. If you could imagine the very, very tallest skyscraper hotel, like in New York City, something that's like 40 stories high, and it's nighttime, and every single window has its blinds open, every light is on, every room is occupied, and every light is on. It's nighttime. And you're looking at this 40-story tall skyscraper, and one person in that hotel goes to the window and lowers the blinds by about 2 centimeters. That's the change in brightness we're trying to measure to see this kind of an event, to see this tiny transit. The other thing that we measure is the time it takes to complete one orbit, because these dimmings of light will reoccur as the planet sweeps in front periodically, once every orbit. And that orbital period, that time between transits, Johannes Kepler told us 400 years ago, is related to the distance between the planet and the star. There's a relationship between the orbital period and how far away the planet is from the star. And if I know how far away the planet is from the star, I know how far I'm standing away from the campfire, then I know what the temperature is going to be. I know if it's going to be too hot or too cold, or just right, right? So that's what we measure. So this is the definition of the habitable zone that you've probably heard a lot about. This is the Goldilocks zone, it's also called. Here is a cartoon of 3 different stars. One is really hot, one is kind of in between, and one is rather cool. The blue shaded region around each one is where the temperatures are too cold. The red shaded region is where the temperatures are too hot, and the green shaded region is where the temperature is just right. Okay? And it's different for each of these stars because this is a blazing hot campfire. You have to be further away. And this is a weak campfire. You have to cozy up next to it, right? And so the orbital period of a planet here is going to be much shorter than the orbital period of a planet over here. Okay, so I want to show you what Kepler has discovered so far. And to do that, I'm going to show you a scatter plot. Have you kids studied scatter plots in school? Okay. Down here we have orbital period, this time between these dimmings of light. And up here we have the size of the planet. So if a point is way up here, it means the planet is really big. If the point is way over on this side, it means the orbital period is very long. Okay? This is the size of Earth, Neptune, and Jupiter. Here is one point in this scatter plot, and that point is bigger than Jupiter. All right? And it's orbiting around 10, 20, I can't read it on the distorted scale, but it's some tens of days orbital period. And that was the first one that was discovered in 1989. It may actually be too big to be a planet. But what I'm going to do is I'm going to step forward and I'm going to add points to this scatter plot as they were discovered. So every point represents a planet, an exoplanet that was discovered. Okay, we're going to add them to this diagram. And so the next one wasn't discovered until 1995. And as the years tick by, down here in the right-hand corner, we get more and more discoveries. Most of them are kind of up here around Jupiter sizes, right? Interestingly, some of these planets have orbital periods that are just a couple of days. Like, look at this cloud of points right here. The points have different colors. These pink points were planets that were discovered by this transit method that I told you about, this dimming of light. We're calling that the transit method. The blue points were discovered using this Doppler method, this wobble method that I told you about. And here I'm calling it velocimetry because we're measuring the velocity of the points. So this is what the situation looked like in 2009 on the night before Kepler launched. Okay? We had lots of planets that are around Jupiter sizes. We kind of had a cluster of them over here at orbital periods of a couple hundred days. We had this other really weird cluster of giant planets orbiting their star in just a couple of days, which is really weird. We don't have anything like that in our own solar system. Jupiter and Saturn and Uranus and Neptune are way out there in the outer reaches of the solar system, right? Okay, well, let's clock it forward and see what other discoveries were made not taking into consideration Kepler's. Kepler's discoveries are going to be yellow, and I'm going to add them at the end. So as Kepler was flying, taking data, 2010, 11, 12, 13. More and more discoveries were made. You see that there are some Doppler measurements pushing down to smaller sizes. And now I'm going to add all of the discoveries that Kepler has made in this 4-year period after actually taking about 3 years worth of data.
Wow.
It's a lot, huh? It's a lot of new worlds there. As I said before, there were about 800 exoplanets that were discovered by other teams. Kepler, with 3 years of data, has discovered over 3,500 planets orbiting other stars in our galaxy in this one tiny little patch of sky about the size of my hand. But what's really marked about this is how different the distributions are, right? Remember, we had a cloud of points up here and a little cloud of points up here. Look at where all these discoveries are. We had blinders on. And our blinders have been lifted with this new piece of technology. We didn't know that there were planets in such abundance, small planets in such abundance. We didn't know until we had the sensitivity to see, until those blinders were lifted by this new piece of technology that we put out into space. Okay? So 3,500 planets, 85% of them are smaller than Neptune. These planets kind of between the size of Earth and Neptune are the most abundant type of planet in the galaxy, it seems. And what's weird about that is that we don't have any planets in our own solar system that are between Earth and Neptune. We have Mercury, Venus, Earth, Mars. Earth is kind of the biggest of the terrestrial-like planets. And then we jump to Neptune, Uranus, Jupiter, Saturn, right? We have nothing in between. And yet those seem to be the most common type of planet there is in the galaxy. Around Earth size down here, there are over 600 new Earth-sized planets that Kepler has discovered. Between 1 and 2 times the size of the Earth, we have about 25 that are smaller than twice the size of the Earth and in the habitable zone. I showed you what the data looks like. Remember, I showed you a picture, that first image with all of the stars salt and peppered over the image. And when you zoom into it, it just looks like this. It's just kind of black and white pixels, right? Every square is measuring light from this one star. It's spread over many squares, and we just add up all the light in those squares, and we get a brightness measurement. And every white dot that you see in this plot is one brightness measurement. Kepler takes a brightness measurement of 150,000 stars, actually 170,000 stars, simultaneously once every 30 minutes, and does so without blinking, and did so for 4 years of its life. So this is what we call a light curve. It's simply brightness as a function of time, just like you saw in that cartoon with the green trace underneath it. This is for a planet called Kepler 10, little b. Kepler 10 is the name of the star. And the little b indicates planet, the first planet that was discovered orbiting this star, this particular star. And remember I told you that the depth tells us something about the size of the planet, and this depth tells us that the planet is only 40% larger than Earth. It's very, very tiny. So I'm showing this to show the progression from the pictures that we take to the brightness measurements, and then down here in the bottom right-hand corner, it kind of almost looks like we took a picture of this planet, but we didn't. What we do at this point is we take this information, we measure its size, we measure its orbital period. I say, well, okay, given this orbital period, it's this far away and it's going to have that temperature. And I can, if I have its mass also, I can get the surface gravity and I can get its age. And I put everything that I know about all of these planets together and I give all of that information to an artist. And the artist says, okay, well, it's going to have this color, and it's going to have this size, and he makes it come to life. And so down here in the bottom right-hand corner, we have an artist's conception of one of the planets, not actually this particular one, but one of the planets. So I'm going to show you some of these artists' conceptions of a small number of these worlds that Kepler has discovered so far. This is an animation of Kepler 10b. This planet that's 40% larger than our own Earth is orbiting 23 times closer to its star than Mercury is to our own sun. It's a blowtorched planet. It's very, very hot. The temperatures there are higher than that required to melt iron. Okay? We know its size, we know its mass. It's about 4 times the mass of our own Earth, a little bit less. We know its surface gravity. You would weigh about twice what you weigh on this planet, on Kepler 10b. We know that it's old. It's orbiting a star very much like our own sun, but it's very old. It's about 10 billion years old. We think that because it's so massive, it could still have plate tectonics. It still has some internal heat. But what's really interesting about this planet that orbits its star once every 20 hours is that it has an ocean. In fact, one whole hemisphere is an ocean. Larger than the Pacific Ocean, an entire hemisphere, but it's an ocean not of water. It's an ocean of lava. So we call these lava worlds because they are so extremely hot, rocky, and therefore molten on that star-facing side. That's Kepler 10b. Other interesting things we have found planets that have not just one sun rising in the east and setting in the west, but 2 suns rising in the east and setting in the west. George Lucas was right. After all these years, we finally proved that George Lucas was right. Here's Luke Skywalker's home world, Tatooine, with 2 stars rising or setting. I'm not sure which it was over there. Maybe it was setting. Ends up here as an artist's conception of a planet called Kepler 16b, which has 2 stars, one more massive than the other, one hotter than the other, rising and setting. And these 2 stars are gravitationally bound. They're orbiting one another. So not only do you have these 2 stars rising and setting, these 2 stars are continuously dancing around, moving, swapping places as they go across in the sky. So some people have nicknamed this planet Tatooine after the Luke Skywalker world. We've also found planets orbiting stars in star clusters like the Pleiades. These are groups of stars, families of stars that were born out of the same nascent cloud of gas. They're still kind of loosely gravitationally bound. Therefore, you have a higher density of stars. Our own sun doesn't have any near neighbors like that. But you have star clusters that do have near neighbors. They're dense enough that they have near neighbors. And this particular one has many near neighbors. So when you look up into the sky from this planet, you see a jewel box sky, right? Not the distant stars that we see from our own planet, but you see a jewel box sky. This is, there are 2 planets in this star cluster that happens to be in the Kepler field of view. We have found worlds that are just the right size, talking again about Goldilocks planets. Kepler 20 is the star, and little planet E and little planet F. One is just smaller than Venus and Earth. One is just larger than Venus and Earth. Here are Venus and Earth for comparison. But these stars are orbiting much too close to their host star to be habitable. They're way, way too hot. You wouldn't want to live on Kepler 20e or F. And we have found worlds that are just the right distance from their star. The temperature is just about right. They're getting about the right amount of energy, but it's probably too big. This is Kepler 22, little b. It's about 2.4, so more than 2 times bigger than the Earth. And when you get to be that big, you start to glob on these hydrogen and helium-rich gases that make gaseous and or icy envelopes. So this planet probably doesn't have a rocky surface like we're used to thinking about. It's probably too big. Some people called this, in the newspapers, they wrote about this as if it were a super Earth, which implies something really big, rocky, lots of real estate, or a planet like Earth just scaled up in size. It's actually probably more like a mini Neptune, okay, which implies something completely different, more like an ice world, something that has a lot of hydrogen and helium in its envelope. Let's see, and just this last year, last April, we announced the discovery of Kepler 62 E and F. These are 2 planets, not just one, 2 planets orbiting right smack in the middle of the habitable zone of a star slightly less massive than the Sun. Kepler 62e is about 1.6 times the size of the Earth. And then if we go out a little bit more, Kepler 62f is 1.4 times the size of the Earth. And they are both in the habitable zone. So here's a cartoon. The planetary system actually has 5 known planets. It has 3 orbiting interior, and then these 2 out in the green shaded region. One thing that I didn't say, Kepler 10b, that lava world that I showed you, it was 40% larger than the Earth, right, in its size, and about 4 times more massive. Well, if I have mass and if I have radius, I can calculate mass divided by volume. Mass divided by volume is density. With density, I can tell if it's a gas giant or an ice world or a water world or something actually rocky. And Kepler 10b was the very first rocky planet known to humanity orbiting a normal star outside of our solar system. The very first. And even today, we only know of a small number of these worlds that have both mass and radius determined. And we don't have a mass determination for Kepler 62f, this one out here. But it's 40% larger than the Earth. We know of at least a few other examples of planets that are 40% larger than the Earth that are rocky. So chances are Kepler 62f is also going to be rocky. And again, it's right in the middle of the habitable zone. So things are looking pretty good for Goldilocks over here. I think she even stopped eating her porridge. Here's a schematic just comparing the Kepler 62 system to our own solar system. You see the habitable zone up here is tinier, it's closer in than it is for our solar system because its central star is a little bit cooler than our own sun. It has 5 planets. These are their relative sizes, and here they are compared to Mercury, Venus, Earth, and Mars in our own solar system. So here's E and F, the ones that are in the habitable zone. Okay, well, I told you that Kepler's primary job was to figure out what fraction of stars have potentially habitable planets, right? So that's kind of a statistics game, right? You're kind of like doing a census. It's like when the census taker comes and knocks on doors to find out how many people are living in your houses, right? We're taking a poll. We're taking a census of the galaxy to try and find out how many planets there are of different sizes. And so here we've got a bar graph that shows those statistics based on 2 years of Kepler data. And so it's broken down by size from the Earth-like planets, super-Earths, mini-Neptunes, and then actual Neptunes and gas giants. And the mini-Neptunes, super-Earths, and Earth-sized planets are all pretty common. The giant planets are not. And that's because These statistics are for planets that have orbital periods shorter than 85 days. Mercury, in our solar system, has an orbital period of, does anybody know? 89 days. So this is the statistics for planets orbiting within what would be Mercury in our own solar system, Mercury being the very closest planet to the sun, right? So it's no wonder that the statistics look very different. It's no wonder that there aren't a lot of gas giants in these very short orbits. We don't have any of those kind in our own solar system. In fact, we think that they must form far out from their parent star in order to have these hydrogen, helium-rich envelopes. So this is not too much of a surprise. The other thing that we have learned so far, analyzing this first half of this data, has to do with the class of stars called M-type stars. Here are several balls, and the letters represent different kinds of stars. O, B, A, F, G, K, M. Do you know which one our sun is? What type of a star is our sun? Does anybody know back there? No. No. Our sun, I'll give you a hint, it's kind of in the middle. Yes? F? No, you guys are getting close. You're dancing all around it. Come on, it's a G, yes, exactly. Our own sun is a G-type star, kind of in the middle, but you see some stars are much bigger and some stars are much smaller. We do have an interesting result about the M-type stars, which is this tiny little one right here. You can imagine that the Goldilocks zone for an M-type star is going to be very close, right? It's like a really weak campfire. You're going to have to stand really close to it to be warm enough, right, for life. And if you're standing really close to that M-type star, the orbital period is going to be very short. So in this first 2 years of data, we can already say something about planets in the habitable zone of these cool M-type stars. And we've looked at that. Here's another cartoon also showing, we left off the O's and the B's, but we've got the A's, F's, G's, K's, and M's. And these are the colors that are represented in this cartoon showing what kinds of stars and how many we have within a certain distance. This distance is about 33 light years, or 10 parsecs, we call it. I should have changed that, sorry. That's about a little over 30 light years. And so these are all the stars we know of in our own neighborhood. Most of them, about 70%, or 246, are M-type stars. In our solar neighborhood, there are only 20 neighbors that are like us. Most of the stars in the galaxy are M-type stars, these cool, weak campfires. And we can already say something about the frequency of planets in the habitable zone around them. And so what we've learned, I'm going to do a little thought experiment with you. If you took the whole Milky Way galaxy, and we're out here someplace, and I'm going to say, okay, how far do I have to go, would I have to travel, before happening upon a potentially habitable world? That's the question I'm going to ask myself based on Kepler data. Well, if I took the whole galaxy and I scaled it to the size of the continental United States, okay, and I stood over here in Washington, D.C., and I said, okay, how far do I have to go across the United States before I come across a potentially habitable world? The answer is just across the mall. Okay? From the Capitol building to the Lincoln Memorial, it's like, that is the Lincoln Memorial, right? Yeah. It's about 2 miles. And that's the scaled distance if you take into consideration what we've learned about planets around M-type stars. Kepler data is telling us that about 50% of the M-type stars have a planet smaller than twice the size of the Earth in the habitable zone. Okay? So 70% of the galaxy are these M-type stars. 70% of 100 billion, that's 70 billion, right? 50% of those are thought to have a potentially habitable world. So you're talking about billions of potentially habitable worlds in the galaxy with this one result alone, and we haven't even talked about the G-type stars yet, which I can't talk about today because we don't have those results yet. You'll have to invite me back in another 2 or 3 years. We'll be able to say something about that. All right, a little bit about the future. How am I doing with time here? I want to leave time for questions. Just a couple of minutes about what the future holds. I talked about this roadmap to finding evidence of life beyond Earth. What we really want one day is a picture like this for another planet, with blue oceans and green forests and white clouds and all of that, right? That's what we'd like to see. It's a ways to get us there. There are many baby steps in between. One preliminary step for these planets that are passing between the star and our telescopes, those planets that are transiting, you get something kind of special. This is a picture of our sun, and this planet in front of it is the planet Venus. This is the transit of Venus. And if you look really carefully, you can see a thin atmosphere embracing Venus. Can you see that? This yellow glow is light from the star that's scattering through the atmosphere. Okay? If we can observe the light, if we can catch the light from the star that's filtering through the atmosphere of that planet, the atmosphere is going to leave a fingerprint on the light that we can detect. And so we have the possibility of being able to see what the atmosphere is actually made of, to know something about that world if there's water. I mean, the objective is not just to find a planet in the habitable zone, but to find a habitable environment to find life. How many of you waved at Saturn last year? Anybody? A few. The Cassini spacecraft, which is orbiting Saturn, studying Saturn, and has been doing so for quite some time, took this magnificent picture of Saturn in our own solar system with its beautiful rings. And it took a picture at a specific time, and it told planet Earth what time it was going to take this picture. And it told us at what time it was going to take this picture because they knew, the scientists that run the spacecraft knew that the Earth was going to be in this picture. Do you see Earth? You probably can't read the words that are pointing to, here's Tethys, one of Saturn's moons. Over here is Mars. Venus is over here. Down here, right there, is the Earth-Moon system. Here it is blown up. That tiny smudge, that pale blue dot is actually us. You were there. When Cassini took that picture, you were standing there doing something. You were probably in school because it happened during the day. Every single person who ever has lived, every single person you've ever heard about, One Direction, who else do you know? Obama, Julius Caesar, everybody you know, Martin Luther King, every single person you've ever heard about lived here, right there, right? This is a picture of us from 90 million miles, I think, away. We want to take pictures of other pale blue dots that are not 90 million miles away. They're 90,000 billions of miles away. And we have the technology to do that. We know how to do that. We will do that. We will probably do that before you guys have your own children. All right? So we will take pictures of other pale blue dots. This is one of these baby steps, one of these intermediate steps. We will catch that light. We will take a spectrum of that light, and we will start to be able to disentangle what constituents are there. Is there water? Is that a habitable environment? Is there carbon dioxide? Is there methane? Right? Things that we will look for oxygen. Oxygen is a byproduct of life, right? Here is that same image blown up. Here's the Earth, and there's our own moon from that same Cassini image. I'm sorry, 900 million miles away. Once we do this, once we can collect light from the surface of a habitable environment, we will look for things that are produced by life. And this is an example. This is a microscopic image of a tiny bubble that's coming from a substrate of algae. This is cyanobacteria, and it's being caught in the process of metabolizing and literally burping a bubble of oxygen. Cyanobacteria creates these little, they burp out this oxygen that we breathe. Oxygen is a byproduct of life. And so we're studying what all of these markers are, this evidence of life, so that one day we can look at the constituents on that planet and see if there is evidence of life, if there's some kind of a biomarker. Okay. Well, we're full circle back to Goldilocks. You know, there was a moral to the story of Goldilocks, right? Moral, what was the moral of Goldilocks? What did you learn from Goldilocks? Anybody? Kids? Maybe not to go uninvited into people's houses. That's probably not a good idea, right? Especially not to eat their food, break their furniture, right? Use up all their stuff. So that's a good moral, right? But I'd like to pose a question. Why did Goldilocks go into the forest to begin with? Right? What made Goldilocks go into the forest? There's a Goldilocks. I think Goldilocks was curious, right? Every human being has some innate curiosity that makes them explorers. All of us are explorers. Every time you go out and pick up a rock, you're an explorer. Every time you pick up a leaf, you're an explorer, right? This human body here, which is this little Goldilocks, is part of this universe, right? This little human body is a portal to the universe, a portal of self-awareness. It's the universe waking up and taking a look at its own self, right? That's what our senses are. And it has made us into these explorers, right? So we can ask, why did Goldilocks go into the forest? We can say, okay, well, the analogy is this cosmic forest that beckons, right? Why are we going out and searching for life? Why am I spending decades of my life looking for planets, looking for evidence of life? You know, I could talk a lot about, I could say, well, you know, our planet has a finite lifetime, right? Our planet's not going to survive forever, right? The Earth has a finite life. We're destroying our planet. That's a whole other separate topic. I could say that it's good for the economy, right? Because going to space creates new technologies which make the economy grow and all that kind of stuff. But I don't think that's why we do it. None of those reasons are satisfying to me, and none of those reasons are what get me up out of bed in the morning. I think that we explore because we have to. I think that when we explore, when the Apollo astronauts went off to the moon and turned around and took a picture of Earth, when we humans saw that picture, compassion grew on Earth, right? When we learned through science that our bodies, my skin, is made out of stuff that was manufactured in the core of a star, all of a sudden, all life is connected. And compassion grows, right? It changes our perspective to explore. It makes our own blue marble, that beautiful image of our planet Earth, seem all the more precious when we're out there looking for other planets and realizing how rare these blue marbles are. Maybe it will make us appreciate our own planet more. Maybe we will learn that we're destroying our planet. Maybe we will learn how to better take care of it. I think that's why we're doing it. I think that's why we must. I also think that by exploring, by going out and picking up that rock, by studying math, by studying science, by exploring the cosmos, our brain changes. Our very brain changes. It makes us evolve into something, maybe something better. So I will end with this quote that was from an essay contest that Kepler sponsored some time ago that says, one day, from the shores of a new world, We will gaze at the sea that took us there, and its waves will be stars. And whether that happens or not, it doesn't really matter, because what I believe is that by having tried, we will be different for having done so. We will be better. All right? So thank you very much. I hope we have some time for questions. Do we have some time for questions? What do you think? Yep. If there are any, I don't know. Are you guys curious about anything? Yes.
Well, I have lots of questions, but
Okay.
I'll limit it to one. There's so much inference that you're doing.
So much what?
Inference.
Yes.
That you're doing,
Uh-huh.
and the margins seem so small. The amount of light that changes is so small.
Yeah.
How do you deal with that? I don't know. I'm not sure what the right word is, but the challenge between inferring and the limited margin for error.
Yeah.
That
And
exists.
what you're saying is that there's a lot of noise. I mean, how can you see such a tiny signal in the noise, right? And that's the whole challenge, right? I mean, the science is very simple. You stare at a bunch of stars, measure their brightness, and wait for one to dim. But it's the error margin that's what's important. We have to do this with exquisite precision, part per million precision. That's what makes this such an engineering feat. If you can squash down your noise floor, the signals will emerge. And that's the challenge of science. Every time we build a bigger telescope, every time we go to space, every time we build a bigger particle accelerator or whatever, what you're trying to do is beat down the noise floor so you can see finer and finer detail. That's what was required. So it's just engineering. Yes?
I want to draw an analogy. In recent decades, oceanographers have searched deep into the ocean to extreme depths, and they found life that they never could have imagined existed. And that life actually creates its own energy and its own light source. And I'm not an oceanographer, but I know that's been going on. My question to you is, and that would not be considered a habitable zone in the ocean.
It has water. There's liquid water.
Right, okay, but by other measures, it doesn't seem to be habitable by what we would think is habitable. So my question to you is, if something like that could happen on Earth in our own ocean, or are we narrowing our perspective by saying a habitable zone for life in outer space has to be what we view as being us?
Yeah, that's a great question. Are we being myopic? Well, okay, there's two parts to that. I mean, the first answer is yes, of course, and by necessity. Okay, and I'll come back to that in a second. With regards to these creatures that you're talking about, like these subglacial lakes, or there is water. So when we took a look at our definition of what habitability means, we tried to find a common definition. We didn't want to exclude any creature that we know about that lives on planet Earth. Every creature that we know about on planet Earth requires liquid water. Okay? If you go to the Atacama, the driest place on Earth, there are some organisms there on the rocks, but they mostly live in a dormant state until they get that fraction of an inch of rain that they get per year, right? And then they kind of do their thing. So every creature that we know about requires liquid water. And so that was the broadest definition that we could come up with. But even that said, it is myopic because we only have one example of life. It could be that not all life is carbon-based. Maybe there are sand creatures, maybe, who knows? But you have to start someplace, right? And we start with what we know until we know more. And then we'll branch out from there. Yes?
When you talked about that section of the sky the size of your hand
Yeah.
with the triangle, who chose that section for this
Yeah.
particular mission, and how was it selected? Or was it just kind of random?
Well, it's your lucky day because I chose it. So why did we choose that particular patch of sky? Well, the spacecraft is orbiting the sun, and it's got to stare at a particular patch of sky all year round. So the spacecraft orbits like this, always looking at that same patch of sky. And so that means that sometimes it's pointed over the sun. And if the spacecraft is pointed too far down this way, then a lot of sunlight's going to get into the telescope. So we had that one constraint. It had to be, over the course of the year, it could never come within a certain angle of the sun. That's one thing. Second, we wanted to observe near the plane of the Milky Way because that's where the star density is highest. We wanted to observe lots of stars. The reason that we needed to observe lots of stars is because we're looking for these aligned systems. We're looking for these dimmings of light that only occur if your orbital plane is aligned so that that shadow sweeps across your telescope. And stars are all aligned in random directions, right? Only like 1% of the stars are going to have the right alignment. So we want a high number of stars so we can find lots of them, plane of the Milky Way. We wanted something that was visible from the northern hemisphere, not the southern hemisphere, because in the northern hemisphere is where we have the Keck 10-meter telescopes and a lot of our ground-based observatories are there. And when all of that was said and done, of course the devil's in the details, right? Most of the work was in the last 1%. We did simulations of the galactic population of stars to fine-tune exactly what angle above the galactic plane was optimum. And imagine, the analogy I can give is, well, let's say that you are trying to take pictures of fireflies at night. You don't want to stare right in front of the San Francisco skyline, right? Because all those skyscrapers in the background are going to confound you. The fireflies are there, but you're not going to see them. But if you look just a tiny bit above, you can still see lots of fireflies and the skyline drops out of sight. So we optimized it that way. All of those things came into consideration. Yes?
If we found like one, would we like move in or something?
What happens when we find one? Would we move in? I think that once we find planets like Earth, once we find evidence of life, I think humans are going to find a way to get us there. Right now, we don't know how, right? If you were to try and send a spaceship at 1/10 the speed of light right now to the nearest star, it would take an inordinate amount of time, well, hundreds of years, right? You could do that, I suppose, but you're not talking about sending humans, right? That's really hard. We don't know how to do that. And we want to get to these places quickly, not over many generations. I don't want to take off and then have my grandkids be the one that get there, right? But I think that humans are going to figure all of that out. And I think that we're going to be motivated even more so to do that once we know, once you can go outside and point to a star in the sky and say, that star has life on it. Right? Aren't you going to want to go? Yeah. In the back?
Are there markers for anaerobic life? The Earth life on Earth was all anaerobic for a million years or so,
yeah.
If I'm not mistaken. And would we be able to detect life if it wasn't photosynthesizing?
Well, the anaerobic life, cyanobacteria is anaerobic. It doesn't consume oxygen. It creates oxygen as a byproduct. So detecting the oxygen, you're detecting it from an anaerobic species, which is the cyanobacteria. But you're right. I mean, they're all different kinds of life, and they're going to produce different biomarkers, and we need to learn what those biomarkers are going to be. Methane is going to be another one that's a common byproduct of metabolism. Farting cows. Sorry. Yeah, but it's not trivial, because there are also geological processes which create the same molecules. So you have to be able to disentangle what's what and understand. What you probably have to do is detect several of them in concert that could not exist by themselves together at any given time unless there were life. But it's actually really a tricky problem. Let me see, right there?
I heard about another mission launching in a few years also to detect extrasolar planets. I think it was called TESS.
TESS, yes. Uh-huh.
What's different?
What's the difference? Okay. And so Kepler is a statistical mission. It's looking at this one patch of sky. It's looking at a cone of the galaxy, right? This like slice of the galaxy out to like 3,000 light years. And 170,000 stars, trying to get the statistics. Now that we kind of have a handle on the statistics, what we want to do is we want to look at the whole entire sky, all around, everywhere, every direction, and we want to find all the planets that are closest, our closest neighbors. So TESS is one step in that direction. TESS is going to survey the whole entire sky, and it's going to look at the closest stars to try and find those that are transiting. It's using the same detection method. It's looking for the dimming, periodic dimmings of light, and it's looking for the transiting systems that are closest. It's not going to find Earth analogs. It's not going to find, it's going to observe each patch of sky for a couple months. So we'll only find planets that are in short period orbits. And it'll look mostly at that class of stars called M-type stars. But what's interesting about TESS is it's going to find nearby systems that can be observed by our next generation space telescope, which is the James Webb Space Telescope, the successor to the Hubble Space Telescope. That telescope is going to be able to do what I showed you with Venus in front of the star, the starlight that's filtering through the atmosphere of the planet. JWST is going to be able to measure it, and it's going to tell us what is in the atmospheres of these nearby transiting planets. So that's what TESS is going to do. It has this symbiosis with JWST. Beyond TESS, there's going to be, it's not funded of course, but one of these days there will be something called a New Worlds Observer, which will also survey the whole entire sky looking for the Earth analogs that are nearby. Yes?
Why is there a constellation on the screen?
Why is there a constellation on the screen? Because that shows, that symbolizes where Kepler is looking. Kepler is looking at one particular place, one particular patch of sky that is tucked under the wing of that swan. The constellation is called Cygnus, which is a swan. You can see it in the summertime. It's right overhead. And the piece of sky that we're looking at is tucked right underneath the wing. Okay? Yes?
But when you were saying Kepler 32b, B was always the first planet that was discovered, is A reserved for the star?
Yeah, we don't use A. The first planet that's discovered is little b. We don't use A because that would refer to the central star. And that's historical. It has to do with binary star systems. It's a historical relic. Yeah. Yes?
How long have you been doing this? How long have you been doing this?
How long have I been doing this? A very long time. I have lots of gray hairs. Let's see. Well, I've been working on Kepler, this project, since before it was even built, for 14 years. Yeah. So it took 9 years for us to get it funded and built and decide where we were going to point the telescope and which stars we were going to observe and all of those things before it even launched in 2009. I came to NASA in the year 2000, and then it launched in 2009. Yeah. Thank you very much for having me.